Welcome back to BIS 121. We're going to go through a couple examples in Chapter 9, examples 9.4 through 9.9, which basically look at, okay, how do we interpret all this data that we get? So we made a scatter plot, as you remember in our last, of all our market value, and we did a scatter plot. We graphed our square footage here and our home value here, and we clicked on one of these to do an add a trend line. We got a best fit linear trend line, and we got this equation in this r squared. The simple way to interpret the r squared is simply to say that basically means 53% of the variance is of the variance in our y value. So 53% of the variance in our price of our homes is explained by the variation of the square footage of the home. Now, the next thing we did is we went ahead and we took a look and we did a data, and we took a look at all our data analysis, and we went down to regression and clicked that, and that gave us all of this stuff, all these regression statistics. So let's go down one by one and make sure we understand what these regression statistics are telling us. So this first section, this first square, the most important thing is the r squared, and of course we already knew that because it gave it to us on the trend line. And again, that means roughly 53% of our variation is explained by the square footage. So the change in home prices, 53% of it is explained by the change in the size of the square foot of houses. This standard error, the book talks about this very, very briefly. The standard error is basically the standard deviation of our sample. And up here we took the standard deviation of our population, all of our scores. And the fact that this deviation is less than this one is an indication that by utilizing the regression, we've explained a lot of the variation away. What you're going to use 99% of the time is this r squared. The next thing it explains to you is it gives you the Anova section. Oh, just so you know, all of these multiple r is r, and then the r squared is just r squared. So if you take 0.73 squared, you get 0.53. The adjusted r squared is used when we do multiple regressions. We'll look at that. The standard error I mentioned is basically the deviation of my sample, and this is the number of observations we have. It also gives us an Anova analysis, which you won't use a whole lot. But what is basically coming into play with the Anova? Remember what Anova does. Anova compares analyzes the variance to determine how much of the variance was between our groups and how much of it was within our groups. And if we have a lot of variance between our groups, that means that there's a statistical difference or a relationship there. So this is degrees of freedom, our DF. This is our squared error. This is our mean. Our F statistic is our statistic for this type of distribution. It doesn't give us a test statistic with this, so this isn't a whole lot of good, but it does give us a significant F, which is basically a p-value. And you can see the p-value is very, very small. So our null hypothesis in all of this is that our slope is zero, i.e., there is no relationship between the two variables. All this is telling us by the p-value or the significant F being very, very small, all that's telling us is, yes, there is a relationship or statistical relationship between these two. The odds of it happening just by chance are almost zero. So, but it's not useful a whole lot because you wouldn't get a good r squared unless you already had a relationship. But it gives it to you, so I thought I would explain it. For the most part, you'll never use this Anova as part of your regression because if your r square is no good, you're not going to use the regression, and your p-value's going to be significant only when you have a good R-squared. The next section gives you the coefficients, gives you the p-value. Notice the p-value is the same as the f. And these are the lower and upper ranges, which I'll show you in a minute of how to utilize that. So long story short, all that's happened here is we can reject, in theory, the null hypothesis that the slope is 0. We have enough evidence, we have enough statistical evidence to say that there is a statistical relationship between the size of the house and the price of the house. Now, it also gives you some of these plots, which are very, very useful. Here's the square foot residual, and these you need to take a look at, because what you want to look for is randomness in my residuals. I want to think of a weather forecaster. You want the weather forecaster, a couple things you want them to be. You want them, ideally they're always perfect, but that's not going to happen. But what you want is randomness in where they miss. Like one day the temperature's a little warmer than what they predicted. The next day it's a little colder than what they predicted. If they're consistently missing it on one side or the other, then that tells us we could probably come up with a better equation. If they're always low or always high, we could come up with a better equation. But if there's randomness in their misses, like sometimes they're over, sometimes they're under, then that tells us that we've probably got a pretty good equation. The other thing you want to look for is, if I look at my whole series of x's, does that randomness continue? Because what you don't want to have happen, again, with the weather forecaster, he's been right for all year, and then the next year, let's say global warming took everything up a notch, and the next year, all of a sudden, where he had randomness here, he no longer has randomness out here. That would be an indication that something is changing, like the global warming, or something's happening. Okay, so that's a good analysis to look at to make sure we've got a good thing. The other piece of output is it gives us all the residual values. Here's the predicted value. This is how much we were off. And this is what's called the standard residual. Now, what a standard residual is, if you remember back to our statistics, it's basically a standard I's score. In this case, because we're assuming that our residuals will be on a normal shaped curve, it's basically a z-score. So remember, a z-score standardizes this score. Most z-scores from -3 to 3 will explain about 99.7% of our data. Now, another thing you want to look for is to make sure they're normally distributed. So what I did is I went up here and I made a histogram. And a reminder of how you do that is you go to data, you go to data analysis, you say, make me a histogram, and you say, okay, and it says, what's the input range? Well, I want all my standard residuals. I gave it my bin numbers, and I told it where I wanted it to be output to. Okay, and that gave me all of this set of data, bin and history, and then I just made a column chart out of it. And let's take a look at this to see if we've got sort of a normal shaped curve. Well, we've got pretty much a normal shaped curve. We're skewed a little bit to the right, but not badly. That tells us these two, the standard residual histogram and the square feet residual plot, tell us if we've got a pretty good, if there are other fits that might be better. It tells us if we've got a good fit for the data. Notice this one way out here more is our one outliner, which we also see up here. We got one outliner that we might want to go look at. I don't know, maybe they've got a swimming pool in their yard. I don't know. But that's worth investigating. The last thing is here I took our square footage. This is so you can give a range. Because if you went into a real estate agent and you said, I want to buy a 1,750 square foot house, how much do you think that'll cost? And they said, oh, that'll cost $93,975. You'd think they were a little crazy. What we did here is we went ahead and we took, notice here, our 95% intervals for our intercept and our square footage. You can take those values, put those into the equation for the low end, put those into the equation for the high end, and now it allows us to say, Well, we're 95% confident that a 1,700 square foot house will cost somewhere between $57,000 and $130,000. So when you walk into the real estate agent, you say, "What's a 1,750 square foot house?" The real estate agent can say, "Well, generally it's going to be between $57,000 and $130,000, somewhere in that range." Oh, so that takes us through all of the examples in the book from 9.4 to 9.9. Basically, how you how you interpret all of this residual regression and residual analysis that you have. Hope that helps. Have a good day.